Welcome to the PowerPoint presentation on EC401 Information Theory and Coding. Myself Anla Kuriakos, and in this session I'll be handling the second module of ITC. So in this module we'll be dealing with the following topics. We'll first see the Shannon's first theorem, which is the noiseless coding theorem. We'll see its relevance. Then we'll move into the construction of the basic source codes, the basic source coding schemes, of which you have to study just two of them, which is the Shannon-Fano algorithm and the Huffman coding technique. And on the third part, we have what is channel capacity, where you will be introduced to the channel redundancy and efficiency. And last, the different types of channels. Even though there are many in your syllabus, we are restricting it to the two types of channels, which is binary symmetric channel and the binary erasure channel. In the part 1 of this module, we will be dealing with the construction of the basic source codes, which includes the Huffman coding and the Shannon-Fano algorithm. And the rest of the topics will be covered in part 2. Now let's move into the next session, which is the construction of the basic source codes. Now before moving into it, let's have a quick recap about source coding. Now it's the source encoder, that block, which converts the symbol sequence emitted by the information source into sequence of bits. So it is a source encoder that maps the symbols into bits. The question is, how is this mapping done? Normally, we assign every symbol with a set of bits. But the problem is, if we assign the same number of bits for every symbol, obviously the length of the sequence is going to be very large. So the basic idea behind every source coding technique is we are going to assign differential bit lengths to different symbols. And what is that based on? We know that in real world scenarios, different symbols occur with different probabilities. There are symbols that occur with maximum probabilities and vice versa. So here, the symbols that occur more frequently will be assigned shorter bit lengths. Whereas the ones which occur with least probability, they are given with more bit lengths. So that is a basic idea, and based on this we have to study two basic source codes, which is Shannon-Fano codes and Huffman coding. Even though there are more, our syllabus is restricted to these two coding schemes. The first source coding scheme that we are going to deal with is the Shannon-Fano coding scheme. Now let's discuss the procedure of this technique. So you will be given a set of symbols and the probabilities with which they occur. So how are we going to proceed further? First, you arrange the symbols in the order of their decreasing probabilities. So you have the symbol with the maximum probability first and the symbol with the least probability as the last entry. Now the symbols are arranged into two groups such that the sum of the probabilities in each group is approximately equal. In the third step, all the elements that are in group 1 is assigned a 0, and all the symbols that fall in group 2 is assigned a 1. Now you have to continue this. That means the first group, if there is more than one element, it is again subdivided into two groups such that the sum of the probabilities in each group is approximately equal. So you keep on doing this, unless and until each particular set has one symbol. So that further subdivision is not possible. To have a better understanding about Shannon-Fano coding scheme, let's take up an example. So given is a question where you have a source which emits 6 different symbols from S1 to S6 and their probabilities are also given. You are asked to construct a binary code by applying Shannon-Fano encoding procedure, and you are asked to find 3 parameters which we'll be considering very soon. So the first step is you are asked to arrange these symbols, okay, in a table such that they are arranged in the decreasing order of their probabilities. So first we construct a table, okay, with the 6 symbols, but they are arranged in the decreasing order of their probability. So S1 with a probability of 0.4 comes as the first entry, S2 with 0.2, you have S5 with 0.2, S4 with 0.1, S3 with 0.07 and S6 with 0.03. So this is how we arrange it in the decreasing order. Okay. Now the second step is you are asked to divide the entry into 2 groups such that the sum of probabilities in each group, okay, they are approximately the same. Okay. So how am I going to divide it? It can be the same, it can be approximately the same. So suppose I divide, one is 0.4, okay. When I add the rest of the entries 0.2, 0.2, 0.1, so when I add them up, it's going to be 0.6. Okay, so 0.4 and 0.6, there's no way they can be equal, but they're approximately equal. So either I can divide this as the first group and all of them as the second group. Okay, or there's another way. The first group consists of the 2 symbols 0.4 plus 0.2, so the net probability here is 0.6, whereas the others will have a probability of 0.4. So we proceed this way. The other one is also correct, you can choose any method that you want. Okay, and after you've divided it into 2 groups, assign the symbols in group 1 with a 0 and the symbols in group 2 with a 1. So that is what is shown here. Zeros are assigned here, okay, and the ones are assigned to the group elements in group 2. Okay, so this is a basic procedure. Now we are going to do the same thing what we have done so far to each and every group. So right now I have this group as well as this group. Okay, now I'm going to do the same thing here. I'm looking at the symbols. I'm trying to divide it into 2 groups again such that they have equal probabilities. Okay. So here, since there are only 2 elements, I have only one way of dividing it. Okay. Such that this has a probability of 0.4 and this has a probability of 0.2. Now I consider this as my next group. So here I can see that there are 4 elements. How will I divide it such that their probabilities are equal or approximately equal? The first one has a probability of 0.2 and the sum of the other 3 elements also will give you a 0.2. So correctly you can divide it into 2 sets. So that is how we are going to divide it. Okay. Now the ones which are on the top of the line, they are assigned a 0, and the ones which are bottom of the line, they are assigned 1s. Okay. Next we look at the groups again. So here there is only one element. Here also there is only one element. I cannot divide it further. Here also there is only one element, so I will not be able to divide it further. Whereas this group has got 3 elements. Okay, so I apply this concept again. So if I divide it such that 0.1 comes here and the next 2 symbols are added, their sum is also 0.1. So I can divide it like this. The one on the top of the line is given as 0 and the other 2 as a 1. Now there are 2 elements in this group. They can be divided again, okay, with a 0 and a 1. Okay, now we have assigned the bits as per the coding scheme. But the question is, what is the exact bit representation of each symbol? So there are 6 symbols. The code words for each symbol is for S1 it's going to be 0, 0. For S2 it's going to be 0, 1. S5 it's going to be 1, 0. S4 it's going to be 1, 1, 0. S3 is 1, 1, 1, 0 and S6 is 1, 1, 1. Okay, so here what can you see? So just see the corresponding code lengths also. Since there are 2 bits, the code length is 2. 0, 1, 2. 1, 1, 0, the code length is 3 and the others they have the code length 4. Now the concept is satisfied here. What we discussed earlier, we said that the symbols with maximum probability, they should be assigned lower code lengths, whereas the ones which occur with least probability, they have to be assigned maximum code lengths. Okay. So with that, we can assure that the average word length is going to be minimal, because the ones which occur with least probability, if they are assigned maximum code lengths, okay, I can make sure that the average word length will be at an optimum level or will be less. So this is how we construct a. Now, in the given question, we are asked to find um, three different parameters, which is average length, code efficiency, and code redundancy. So let's see what it is. We know how to calculate the entropy of the source. Okay, the entropy of the source is given using the equation h of s is equal to sigma I is equal to 1 to q p of si log 1 by p of si. So we know the probabilities of each and every symbol. Okay. So with that, I can find out the entropy of the source. There are 6 symbols. So for sigma I is equal to 1 to 6, probability into log 1 by probability, and I get the final answer as 2.209 bits per symbol. Okay. So this is something that we already know, the entropy of the source. Now this is the table that we have constructed after the Shannon-Fano encoding algorithm. Now the average length, okay, of the given scheme is given by, it's equal to sigma I is equal to 1 to q, okay, p of si into li. So we multiply the probability and length of each and every symbol and we add them up. Okay. So the average length is, the probability of S1 is 0.4, that into 2, plus probability of S2 is 0.2, 0.2 into 2, plus 0.2 into 2, plus 0.1 into 3, plus 0.07 into 4, and 0.03 into 4. Okay. So you find out the lengths of each and every symbol, multiply by their corresponding probabilities, and what you get is called the average length. Okay, and that also you have calculated. Its value is 2.3 bits per symbol. Now bits is another unit for bits. It stands for binary units. It's same as bits. Next, how do we find the code efficiency? Code efficiency, or it's represented by eta. Okay, it's given by h of s by l. So you've calculated your h of s, you've calculated your l. Okay, now the ratio 2.209 by 2.3, what you get is called the code efficiency. So this particular scheme has got 96.04% code efficiency. Now code redundancy is the inverse of this. That means 100% minus your 96.04, or 1 minus eta c is your redundancy. Okay, it's represented by R. Okay, and 1 minus 0.9604 is 0.0396, or I can say that it's 3.96%. Similarly, consider another question with 8 symbols and their probabilities are also given. So here the method or the answers are given. You have 8 symbols and their probabilities are arranged. We divide it into 2 groups such that their probabilities are approximately the same. So the first group will have a total sum probability of 0.5. 1 by 4 plus 1 by 4, you have just 0.5, and the rest of them also has a probability of 0.5. Okay, so we divide it that way, and then we assign the group bits as 0 and 1. Again, we continue doing this such that their probabilities are approximately the same. Okay, and we continue until the further subdivision is not possible. Here you can see that you have 8 symbols and their code lengths are also given. Here also you are asked to find h of s, the entropy of the source, the code efficiency, and redundancy. Okay, code efficiency, you have seen it is. Now the values of h of s and l is given. So please do the calculations and verify whether this is the same answer that you've got. So the eta C is HFS by L, which I get it as 100%, and the redundancy is 0. Okay. Now in certain questions, you can see that they'll be asking you to construct what is known as a code tree. Okay, for this particular encoding scheme. So that code tree is shown. Okay, we start off with a S. Okay, and then we could see that S1 is 0 0. So from S, if I map it, you have 0 and 1. Okay, and S1 was 0 0. So from a 0 again you have a 0 and a 1 getting, these are the branches and these are the nodes. Okay, this is a node, this is a node. From each node you can see that two branches occur. So starting from the main node, it branches as a 0 and a 1, but you can see that the least code is that of S1, least length code, which has a code of 0 0. So from 0 I again branch it into 2, which is 0 and 1. So 0 0, so from the main node, 0 0 is your S1 and 0 1 is your S2. Okay, now to the other branch, we have S3 as 100. So your S3 becomes, you map it, there's a 1. Okay, that 1 is again divided into 0 and 1. The 0 is again divided into 0 and 1, and so on. So each node has a 2 branches associated with it. S3 you get it as 100, S4 is 101. Okay, S5 is 1100, S6 is 1101, and so on. So this is how you construct a code tree. Just remember that from each node you will have two branches, one which stands for 1 and the other which stands for 0, and the branches propagate further and you get a code tree. Now certain questions they'll be asking you to construct a code tree also for the given. Now one more question here, but what is different here is you are asked to construct a ternary code. Okay, till now we had been constructing binary codes, but if the question is you are asked to construct a ternary code again by applying Shannon-Fano encoding procedure, then what has to be done? The basic functionality is the same, but since it's a ternary code, I'll have three symbols. If it is bits, I'll just have a 0 and 1. Since it's ternary code, we call it as trinits. Okay, there we'll have three values, which is 0, 1 and 2. So instead of, first you make the table, and instead of converting or dividing it into two groups, we are going to divide it into three groups such that each and every group have approximately the same probability. Okay, so first, this is how it's done. First we write them in the decreasing order of their probabilities, and it's given that way. Okay, and then we divide it into three groups. So the first one, S1, so it's 0.3, 0.3, and the whole thing is 0.4. Okay, so we divide it into three groups this way. This is the first group, this is the second group, and this whole thing forms the third group with probabilities 0.3, 0.3 and 0.4. Okay, so the first group it is assigned a 0, the second group is assigned a 1, and all the other symbols in group 3 are assigned a 2. So this is how it's going to be. Now this and this, they have only one element each, so I cannot divide it further. Now focusing on the third group, which has got 5 different symbols. Now I have to divide these 5 symbols into 3 groups such that they have equal probabilities. So they've divided this way, 0.12, 0.12, and this becomes 0.16. Okay, so the first one is assigned a 0, then a 1, and then the last group is assigned 2 again. Okay, so this cannot be divided further. Moving on to the last group, that has to be divided into 3 approximately equal probability groups. So that is divided into 0.06, 0.06 and 0.04. Okay, and it's given as 0, 1, 2. So here you can see that this is how your table is going to come, and their approximate length is also shown. S1 has got a length 1, S2 has got length 1, and again, you are asked to find the average length, the code efficiency, and the redundancy. So let's start with the entropy first. But since this is a ternary code, there it is HR of S where R is equal to 3, since we have 3 separate mappings. So here H3 of S, we get it as H of S by log R to the base 2 where R is 3. So H of S you know how to calculate because the source is given and their probabilities, the symbols and their probabilities are also given. So you can find H of S comfortably. But since this is a ternary code, the effective entropy of the source is going to be the obtained HFS by log 3 to the base 2. And the answer is 1.545 trinits or ternary units per symbol. Okay. Now I want the average length. The average length we know it is sigma is equal to 1 to q pi into li. Okay. So we have the table in the previous slide. So multiply each code lengths with their corresponding probabilities and the sum is called L. Okay. Now code efficiency as we have seen is HR of S by L. Okay, we've got it as 99.05 whereas code redundancy is 1 minus the code efficiency value. Here the points to be noted are here the code efficiency increases as you increase the code. It's a ternary code. You can see that the code efficiency has improved. And please remember that whenever you are asked to find the entropy of the source, since this is a ternary code, you have to find HR of S. So now let's discuss the disadvantage of Shannon-Fano coding. Now here, there may be two different codes for the same symbol depending on the grouping of the probabilities. Okay, so we have seen that in the first question, we have seen that the way that we divide it into groups that can differ depending on person to person. So it's the different codes can be assigned for the same symbols depending on how you group the probabilities. Now, the second thing is, it need not be an optimal solution always, okay, because there are multiple ways of grouping the symbols. Don't expect that in each and every case you have the same set of code efficiency and redundancy. It's not. Okay, so whatever the way that you proceed may not be the optimal solution. So if when we are trying to make them into equiprobable groups, care should be taken that the symbol with the highest probability of occurrence will get a code word of minimum possible length. Okay, so this is something that we have to ensure, and that is one. These are the two disadvantages that is normally seen when we consider the Shannon-Fano coding procedure. Now, I've kept this slide to make you understand the disadvantage of Shannon-Fano coding. Here, the question is same as one of our previous questions. Here you can see that the symbols, there are 8 symbols and these are the set of probabilities. Okay. Now, in the first method, we have divided the symbols into groups of 2 such that S1 and S2 are combined together to form the first group so that the sum here is 0.6 and the rest S3 to S7 has been combined to form the second group. There the total sum is 0.4. Okay, so this is one way of proceeding and you know how to do the rest of the steps. And you can see that L, the average length that we get is 2.52 bits per symbol. Okay. Now, the same question can be done in a different way of grouping. Okay, now this is the second way of grouping the symbols. The first, where the first symbol is made into one group and the rest of the symbols is made into group 2. So here it will have a probability of 0.4 and this set will have a total probability of 0.6. Now this cannot be divided further. This group can be divided into 2 sets again. Here you have a sum of 0.32 and here it's going to be 0.28 and so on. Okay. So as we proceed further, it's the same question, but the only thing is the grouping is different. You can see that the average length that you get here is 2.48 bits per symbol, whereas in the previous case it is 2.52 bits per symbol. So it's the same question. Both the slides we have followed the Shannon-Fano coding scheme, but the groupings has made the answers different. Okay, so this is the shortcoming of the Shannon-Fano coding scheme. While making such partitions, care should be taken to make sure that the symbol with the highest probability of the occurrence will get a code word of minimum possible length. Now that is ensured in method 2. Okay, so this is the shortcoming of the. Let's look into the second source encoding scheme, which is the Huffman coding. This is the most popular code as it produces optimal codes always. Let's look into the procedure of how to produce the Huffman codes. First, the source symbols are arranged in the order of the decreasing probabilities as we had done in the previous code also. Now, we consider the two symbols at the end. That means these are the symbols with the least probability of occurrence. If it is a binary Huffman code, we will consider two last entries. If it is a tertiary code, we consider three of the three last symbols and so on. So here, if it's a Huffman binary code, the two symbols that are having the least probability, they are combined to form a new symbol. Okay, and the probability of the new symbol is equal to the sum of the two original probabilities, and the new symbol is now placed in the table such that it is arranged in the order of the decreasing probability. Now the procedure is repeated until we are left with just two symbols, and if there are only two symbols at the last, we assign the 0 to the first symbol and 1 to the second symbol. The code for which each source symbol is found by working backward, okay, and tracing the sequence of zeros and ones assigned to that symbol. So that's how we are going to get the code word. To have a better understanding, let's consider an example. A problem is given where there is a source with 5 symbols S1 to S5 and probabilities are also given. Okay, you are asked to construct a binary Huffman code. Okay, and after that you are asked to find out certain parameters just like in the Shannon-Fano coding scheme. Okay, so the first step is we are arranging the symbols in the decreasing order of the probabilities. Now, since this is a binary Huffman code, I have to consider the last two symbols and consider them or combine them to form a single symbol. Okay, so the new symbol will have a probability of the sum of these two, which is 0.2. So, if I represent it, it's going to be this way. Okay, that means the 0.4 remains as it is, the first 0.2, this 0.2 comes here, and the sum of these two, 0.1 plus 0.1 is 0.2. Okay, just ensure that this table is also in the decreasing order of the probabilities. But the question still remains, where do I place this 0.2? I could have placed it here, I could have placed it here, because all of them are the same value. Okay, now that is again a choice. It depends on the question also. If the question explicitly says that the composite symbol is as low as possible or the composite symbol is as high as possible, if something like that is defined in the question, then you have to place it accordingly. Now whatever we have shown here is using the method that the composite symbol is placed as low as possible. Okay, so even though the other two values are 0.2 and the composite symbol has a value 0.2, it is always placed as low as possible. Okay, now we continue the same thing. We add the last two probabilities and I get it as 0.4. Okay, so it's placed low to the first initial one. Okay, so the 0.2 plus 0.2, this 0.4 is there, this 0.4 has gone here and this 0.2 will come here. Okay, because I have to arrange it in the decreasing order of the probabilities, but the composite symbol will be placed as low as possible. Okay, Then adding the last two ones, I get it as 0.6 and 0.4. Okay. Now, this is how the steps progress. But the question is, how are the bits assigned? Okay, go to the last stage where there are only two symbols and their probabilities. Okay, in that case, start assigning zeros and ones. Okay, so for 0.6 I assign a 0, and then for 0.4 I assign a 1. Okay, it is the same zero point 0.4 that is here. Okay, because it has come from here, so this is this 0.4 is here. It is here also, and this is here also. So now whatever I found out for 0.4, that value is 1. Okay, next 0.6, you can see that the 0.6 were composed from two separate symbols of values 0.4 and 0.2. Now to understand what their bit combination is going to be, I'm going to trace it backward. Okay, so 0.6, when I trace it backward, okay, this will have a 0 and 1. Okay, next this 0.4 is again a composite symbol. From that, when I trace backward, I get a 0 and 1. Okay, similarly, you can see that the 0.2 that I have is a composite symbol which has value, again assigned values 0 and 1. So the question is, how do I create the code word after these mappings are done? Let's look at the first symbol S1. Okay, that S1 with the probability 0.4, the same symbol is here, the same symbol is here, and the same symbol is here. Okay, and the value assigned to is 1. So S1 will have a value or code that is 1. Next, S2. It is the same S2 that is here, okay, from here to here, okay, and here to here. So this is the path. Okay, from here, 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 and here. So how do I trace the path? S2. S2 means the probability is 0.2. So I have to reach here. Okay. So how will that be traced? 0, 1. So that is how the S2 comes. Next is S3. S3 with a probability of 0.2. So if I map that 0.2 has come here. So I have to reach till here. Okay. Now map the path. Again, it's going to be the 0.6. So if I take it 0, 0, 0. Okay, so S3 is 0, 0, 0. Now S4. S4, the value is 0.1. Okay, but that itself and the next one is combined. So 0.1, if I trace it, it's going to be like this. Okay, so it's going to be 0, 0, 1, 0. Okay, so the answer is 0, 0, 1, 0. Similarly, S5, you can trace it back to be 0, 0, 1, 1. Okay, now after you have constructed the code word, see what is the code length for each symbol. Okay, so here you can see S1 has a symbol, I mean length 1, S2 with a length 2, S5 with a length 4, etc. Now here again I am repeating this type, or the method 1 is such that the composite symbol is placed as low as. Now the question also has a few parameters which has to be found out. HFS, we know what is the equation. Since there are 5 symbols, sigma is equal to 1 to 5, the probability of each symbol into log 1 by the probability. This is the equation for entropy. Okay, and the value for this particular question that we get, okay, find it out. Then you know how to find the redundant efficiency eta, which is given by h of s by l. Okay, and then you have the redundancy, which is 1 minus eta. Now the question also has a parameter called variance. Please do write down the formula. Variance is equal to sigma is equal to 1 to q pi into li minus l the whole square, where li is the length of each symbol and l is the average length. Okay. Now, if the same question, the previous question, if we try to do it using the second method, where the symbol is placed as high as possible, composite symbol is placed as high as possible, then we can see that the assignment changes. Okay, here you can see that zero point 0.1 plus zero point 0.1 is 0.2, but instead of saving it as low as possible, we are going to take it to the highest position, where there are other 0.2s. Okay, so still the symbols are arranged in the decreasing order of the probabilities, but understand that the composite symbol is placed as high as possible. Okay, now a point 2 is placed here. Now let's add the last two probabilities, which add to zero point 0.4, but zero point 0.4 we keep it as high as possible. Okay, and then you have this zero point 0.4 here and this zero point 0.2 here. Now I add the last two probabilities, which is zero point 0.6, and that is taken to the highest position, and zero point 0.4 comes here. Okay, now you assign the bits. Zero point 0.6 is assigned a 0 and zero point 0.4 is assigned a 1. Since this is a composite symbol, that I have to propagate. So this is a 0, this is a 1. Here this is the composite symbol, so that has to be given as 0 and a 1. Then you have, this is the composite symbol, so it is 0 and 1. So how do we assign the bits? In case of S1 zero point 0.4, that 0.4 comes here, zero point 0.4, and it has come here as a composite symbol. Therefore the code word for S1 is 0 0. Okay, next S2, the 0.2 has the 0.2 is a probability. To trace it, it was here, it's a composite symbol and it is given here, and then you have the 0.4 here. Okay, so the value for S2 is 1 0. Okay, next S3, the 0.2 is here, that was added to make 0.4, and that is here. Okay, so if I trace it back, 1 1 1 1, that's it. Okay, next is S4. S4 zero point 0.1 is a probability. It started off from here, 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 and then it's 0.6. So the value is 0 1 and 0. Okay, next is S5 zero point 0.1. It was added to be 0.2 here and then here. So the value is 0 1 and a 1. Okay, so 0 1 1. Okay, so that's how the code words come, and their lengths are also written down. Let's look at the next question. Given a source with 8 alphabets A to H, and their probabilities are also given, you're asked to construct a compact binary and ternary code, and you're also asked to find the code efficiency, draw the code tree for the ternary code. Okay, now we are not going to discuss the binary Huffman coding again, because we have already seen, just giving you the details of the code. Okay, and these are the code lengths that you get, the codes and the code lengths that you get. Now to the ternary code, as that is something that we haven't taken up till now. Now before going into the ternary code, there is one important formula that you need to know. Q is equal to R plus alpha into R minus 1, where Q is a number of symbols, R is the base. So here, since it's a ternary code, your R will be 3. Okay, so your alpha, which is a constant, that should be always an integer. That is a must. So if we substitute the given details in the given equation, 8 is equal to 3 plus 2 alpha. So when I compare that, I get alpha as 2.5, which is not an integer. So before starting to do the coding, please make sure your alpha is an integer. So you will have to increase the number of symbols by a factor of 1, and then you proceed till you get alpha as a integer. So the number of symbols, if I increase it to 9 from 8, okay, you can see that 9 minus 3 is 6, 6 by 2, I get alpha is equal to 3. So before actually starting to do the coding, Huffman coding, add one dummy message symbol so that your alpha becomes an integer. Okay, now let's look at the table. We had 8 symbols, but to make alpha is equal to an integer, I add a dummy variable and with a probability of 0. Now what we do is we group, since it's a ternary code, we are going to add the last or the least 3 probabilities. So I'm going to add 0.05, 0.02 and 0, and that is the sum, the composite probability is taken to the next table, and then the whole procedure continues until you get the last 3 symbols. Okay, now we have got the last 3 symbols. Mark it as 0, 1 and 2, and then trace it backward just like we have done for the binary case, and then you can write the final codes corresponding to each of the symbol and their code lengths can be found out. So these are the codes and the code lengths. Just see the codes. You can see that there are 3 different alphabets, which is 0, 1 and 2, and the combination of these will be the codes. So since there are 3 alphabets possible, which is 0, 1 and 2, your length will be considerably less when compared to the binary Huffman coding scheme. Now let's look into the drawbacks of Huffman coding. This scheme is impractical for real-time applications, okay, because the source symbol probabilities need not be known in prior. Okay, so that is one disadvantage, and the second drawback is it's not the best choice for a source with memory. Here we assume that all the symbols are independent of each other, and that's how we proceed on with the technique. But if there is a source with memory, we cannot assume that the symbols will be independent anymore. So this is not a good technique for sources with memory. So these are the 2 drawbacks when we consider Huffman coding. With that, we have come to the end of part 1. Thank you.